Hey everyone, this is Dr. Walker. Let's look at a second example from v016C. It's called motion in a plane. We'll get more practice using the kinematic equations here. This is also a two-dimensional problem, but if you have a three-dimensional problem, it works the same way. You just add that z direction. Problem says a particle moves in the xy plane, and we can see the path of the particle here. Starts from the origin at time 0, with an initial velocity having an x component of 20 meters per second, y component of negative 15 meters per second. And then we are given the acceleration, which is only in the x direction. So if we were to write the initial velocity in vector form, right, remember we can just write the x and y components separately. We would put vx I hat plus vy j hat. Right, that's how we write the velocity vector. There's no z direction here. So if we wanted to, we would write 20, and you can write the units, but I'm just going to skip the units. 20I minus 15j. It's all in meters per second. I'll put that over here. And the acceleration vector is only in the x direction. Does not have a y component, so it's just axi. So it's just 4 I hat meters per second squared. Okay, so now how do we find the total velocity vector at any time? So we're looking for final velocity as a function of time. We have v initial, a, and we know that time is going to be a variable. So we know that we can just use the kinematic equation that has those variables. So go ahead and write it down. The equation is Vf equals V initial plus AT. All right, we didn't get to practice using this in the lecture video, so that's why we're practicing using this now. So the way that it works is we can write it in unit vector notation. We can write this as V initial in the x direction plus ax time. We can say this I hat plus all of the same thing in the y direction. V initial y plus ayt, all of this j hat. Because remember, a vector can be written in unit vector notation by just separating the x and y components like this. So now just plug in everything that we know. All right. So, and I actually should have put v initial here. I forgot to do that. All right. Okay, so we're ready. V initial x is the 20 plus ax is the 4 t I hat plus v initial y, which is negative 15. Ay is 0, right? Because we only have acceleration in the x direction. So this is 0. So that's all there is to using kinematic equations, in this case in 2 dimensions. We're just writing the final velocity, and we can see that it depends on time in the x direction. Whatever time you have, you could just put it in and get a value for v final. Does not depend on time in the y direction, and it is fully written as a vector in unit vector notation. Let's take a look at part B. It says calculate the velocity of the particle at time equals 5 seconds. So all we have to do for this one is plug in the time, the 5 seconds, into the equation that we just found. I have it written here already. This is the equation that we just found. Now we just have to plug in 5 for the time here. So we're going to have 20 plus 4 times 5, right, which is 20. I minus 15j. So it's going to be 40I minus 15j. So at that particular time, after 5 seconds, that is going to be the velocity vector at that particular time. So perhaps in this picture, perhaps this is 5 seconds. Well, that red vector would be represented by this right here. Let's take a look at the last part of this problem. It asks us to find the position vector at any time t. But before we do that, I think I forgot to write my units, so don't forget your units. You can put them after each number or just put everything in parentheses. Don't forget your units. All right. So now we have to find a position at any time t. So to do this, we're just going to use the kinematic equation that gives us position at any time. Now, we are starting from the origin, so that means that the displacement vector, right, is equal to RF, because delta R equals RF minus R initial, but R initial is 0 because we're starting at the origin. So we can write the kinematic equation like this if we want, delta R, the way that I wrote it in the lecture notes, delta R v initial t plus 1/2 at squared, vector notation. And we're going to split up the x and the y. So let's write all of this in the x direction. So we need the x component of v initial, which we said was 20, times time, plus 1/2. We need the x component of a, which was 4, times t squared. So this is all of the x component of this. So we multiply by I hat, and then we do the same thing for the y. So v initial and the y is negative 15 times time plus, but the y, right, is 0. So plus 0, we don't have a y. So that is going to be it for the y direction. So the position does depend on time, right? The velocity depend on time because our acceleration wasn't changing, but the position depends on time because we are changing position. We can simplify this slightly. We can write 20t plus 2t squared times I, and then we can just say minus 15t j. And we know that all of this is going to be in meters, so we can plug in our units. So this equation will give us the position at any time. You just would plug in your time for t, and that will give you the position at that time.